half of the morning session, and Denis Sigurov from Siberia is going to talk on Volterra integral equations of the first kind with jump discontinuous kernels.
Okay, thank you very much for the introduction. First of all, I would like to thank the organizing committee of this excellent meeting and for invitation of me, specifically Professor Malcolm Brown. It's really an honor to be here. So let's start. So I will be talking about the Volterra integral equations of the first kind with a jump discontinuous kernel. But the kernel has basically special kind of discontinuities. So outline of the talk. So first I will give the problem statement, then I will discuss the regular case when the solution of such an equation is unique. Then I will be talking about the asymptotic approximation of the solution. Then I will discuss the singular case when the solution is not unique, and it may depend on the free parameters and also on logarithms, basically. And then I will mention some generalization possible and switch to numerical solution, which we just basically started to deal with. So that is the equation I'm going to talk about. And the kernel actually is like this. So basically it's experience the jump discontinuities on the special curves, on special continuous curves like this. So how it looks like. So if you will draw T and S, here will be T equal to S, and there will be curves. So alpha 0 is T itself, then alpha 1 of T, alpha 2, etc., alpha n minus 1 of T. So put here tau, yeah, and here is a T capital. So, and so as you see, basically the kernel is defined on this. So here will be K1, etc. Like this, all kind of special kernel. And all the input data enjoy such properties. Basically, all these alphas are, and source f is from C1, and all these functions, ingredients of the kernel, are have continuous derivatives with respect to T for Ts from the closure of this Mi. On the diagonal, the kernel is non-zero. That's quite natural. And on the origin, all these alphas are 0, and they are in perfect order. So there is no intersection, and they are like this. And also, I would need them to increase, at least in the small neighborhood, from the T from 0 to tau. And all the derivatives in 0 are also in this order. So it's quite good conditions. So you would ask why we need to study this equation. So it looks like quite special. So the applications of such equations involves basically evolving, so-called evolving dynamical systems. And it's actually related to vintage capital models in mathematical economics, also related to optimal replacement of equipment under technological change and rational harvesting of biological population, and also demographics. So, but so far all these models were including only basically where all the k's are 0 except of kn. So all this is 0, and it's only defined on this. So I will give the brief overview what have been done before and why we can extend this model to the basically full. So what the methods we use? So basically we employ the theory of functional equations. So I would refer here to the classical book of Gilfond, and power logarithmic asymptotical expansions, and the method of steps from delay ODE, and the conventional successive approximation methods. For numerical solution, of course, we'll use some quadrature rules. Okay. So this is a would call the main power partition of this piecewisely defined kernel. So far, this equation, linear equation, was quite heavily studied. So the main contribution had been done by, I would say, Denisov and Lorenzi, and also my supervisor in my PhD studies and collaborator, Anatoly Solomonovich Apartsin, who wrote this very good book, where there is a very good introduction and an overview of the results what have been done on this specific type of equation, including, of course, the numerical solution. I would also refer to our nowadays American colleagues Khitonenko and Yatsenko, who wrote a number of books concerning such kind of models, where actually it could be also this alpha is unknown. I assume it's known. Yeah, and that's more or less it. So I consider the generalization and new problem statement is as follows. So I already mentioned this, so we can write it in this form. And so my talk is mostly based on these two papers. One of them is published in Differential Equations last year, and another is a couple of years ago. Introductory. So let's start from the very simple case. So we consider that the kernel is like this. And by differentiation, we can reduce the problem is basically to this special functional equation. And we can observe that this solution actually satisfies this equation. And it has one free parameter and also logarithms. So next steps, we will understand why is that. So let's first deal with the local solution, and then we'll expand it on the full set when we have all the data. So we differentiate our equation and we get this formula 2 and make this notation which we would need. So by this means we see we already extracted the x from the integral, which is good. And we are basically reduced our first kind Volterra integral equation. So I forgot to mention that it's actually ill-post, and it's problem, and it's of course it's known subject from all the people who works in inverse problems. Okay, so and we reduce this problem to a Volterra integral equation of the second kind, like this, where operator A is we call it the functional perturbation operator, which is defined as follows. And the B is a Volterra operator of the special form like this. So we use this notation. Well, and the source already like this. So and the kernel, of course, we need Kn to be non-zero. So because we basically make it inverse. So the objective. So we need to obtain the sufficient condition for existence of the local solution. Basically, we need to prove some construction. That's what we are doing. So we make this such a notation. So this dt, d of t is defined like this. So it's basically derived from here directly. And we also use quite a standard approach. We use an equivalent norm like this, so that the Volterra integral operator could become contractive. So we can use this, and basically making such an assumption that in d in 0 is less than 1, we can also prove this. And finally, we can prove this construction. So basically, we can formulate the sufficient condition for existence and uniqueness of the local solution. So let for t in from 0 t, the following conditions are fulfilled. So the kr should be continuous, and all this input data, well, alphas, these curves have continuous derivatives with respect to t. On the diagonal, kernel is non-zero. All these guys are in perfect order for t from 0 to t. And in the source, basically alpha I is 0, and this condition is also fulfilled. Then our equation has a unique local solution. Well, it's only local. So back to our equation. So in this case, d of t is just 1, and so this condition is not fulfilled, and solution is not unique. So that's one of the ways how to check it. So now about switching to global solution, we can formulate such a theorem too. So the sufficient condition of existence and uniqueness of the global solution. So let all the conditions of the previous theorem are fulfilled, and moreover, we assume that this minimum, so basically this distance, okay, like this, h, is bigger than 0, then our equation has a unique global solution. Let's see. So here, this is the result from this article, which will appear in automation and remote control. So this is again a picture. So to prove this theorem, we need to have this lemma, which is telling us that let alpha basically map from 0 t to L plus. Alpha of t is from C1. Alpha in 0 is 0. Also this condition of the derivative of alpha is fulfilled. And let this h from 0 to t, that we can actually split all this 0 t interval on the unification of this ik. So and if this alpha of t is in this estimate, and this condition is fulfilled, then we have such an formula, basic inclusion of 4. So the proof is basically based on induction and the mean value theorem. So I would skip it. It's quite easy to prove this result. And back to the theorem 2. So we now have this nice lemma. We are going to use it. So then basically the local solution already exists on 0 t due to the condition of the theorem 1. And let delta bigger than 0, such as all this interval is presented as the unification of this I0, etc. k. And alpha is maps 0 tau, of course, to 0 tau prime, which is less. This is just comes directly from the geometry of this domain. And then for t from tau to t capital, due to the lemma conditions, we have such an estimate. It allows us to select delta which is less than h, such as condition 6 is fulfilled. No condition, but inclusion, basically. So inclusion 6 allows us to extend the local solution x0 into the whole interval tau t capital with a step delta using the method of steps. So basically, we put the known on the right-hand side and solve this on the every step the solution, the Volterra integral equation of the second kind. So with the right-hand side already is a known. So first it will be known the local, then we can continue this, and eventually we will get the solution on the whole interval where all the input data we have. Okay, so in case of d in 0 is less than 1, the global solution exists and unique. Local solution is constructed by successive approximations and continued by the method of steps, with a successive approximation on each step of this method. So in the theoretical interest is basically to study the case when the d0 is bigger or equal to 1. So we assume the condition A. So this polynomial, like a pi, like this, powers of t and s, and this for the source data also we have the power series, and the same story with all these alphas. And the following can estimate whole. So basically, this stress on this m, we would need it. Yeah, and so if you relate this supplementary condition on the local smoothness, basically. So it's on this slide, so we will need this condition B, and the estimate is true for big enough m. So, and so now we assume that condition is d in 0 is less than 1 is not fulfilled. And we assume this condition C, like discrepancy basically. And we can formulate these results on theorem 3. So let x hat be the known function such as C is fulfilled, it's true, for m less than this n star, which is here in the numerator. Then equation 1 has the solution as follows, where U is unique and can be constructed by the means of successive approximation method. So basically for U we have this equation star, which already has a unique solution. It's easy, basically quite easy to prove by proving that its homogeneous equation has only trivial solution. And I call this as it's a definition. Basically, the equation 1 has a unique solution. We can call it the regularization of the equation 1. And this function x hat is the approximation of the solution of our given equation. Okay, the question remains. The question remains how to construct x hat to meet the condition C. Okay, the idea is to construct it as a power logarithmic asymptotical expansion. And we will need an additional, of course, smoothness of the all given functions according to the condition A, since we need the Taylor coefficients. So, but no need in this condition. So the theorem 4, basically, which is a relaxation of the condition of D0 is less than 1. So let conditions B and C are fulfilled. Let me just remind you what is B and C. So this is C and this is B. Estimate is true. And let this, I call it the characteristic equation. So basically, it's fulfilled. So, but J is not 0 for G, and then including the 0. Then equation 1 has a unique solution in C. It's m greater than n. And moreover, for n, for t goes to plus 0, the polynomial xm x hat basically is the mth order asymptotic approximation of such a solution. Okay, so the proof is actually quite straightforward. And now, how actually we can construct such a power logarithmic asymptotic of the solution? So again, we search the approximation of solution as follows, and we find this coefficients xj using the method of undetermined coefficients, and we must solve the recurrent sequence of the linear algebraic equations like this, where m0 will be just f prime 0. So in the, again, stress on this characteristic equation, it's like this. Okay, so this is a case when the solution is unique, but if we would meet J star when the B of G is 0, then the coefficient of the power logarithmic expansion is the solution of the difference equation like this. So as you see, basically the key ingredient of this theory basically is the solution of the functional equation. So basically if we consider, for example, like a functional equation of like this, which is, as you notice, the case, where A and B capital are just constant, and alpha 1 and alpha 2 are constants also. And we basically will be looking for our solution using the method of undetermined coefficients, where the coefficients themselves are functional, so they basically depend on the logarithms. So basically, the right-hand side we will write just an expansion of y, t power y, and the solution x of alpha of t basically will look as follows. So here is our coefficients. So here z is just by definition is logarithm of t, and a is by definition is logarithm of a. And we will substitute into our functional equation. We would get nothing else as our characteristic equation. Indeed, so basically if we substitute this guy, what we are getting? We are getting A. So alpha 1, alpha 2 is the power of A. Okay, I'm just writing it for each I, just omitting this summation. So on the right-hand side will be this, just this coefficient. So and we equate the basically the coefficients which are stands next to the t in the power of I, and we are getting our characteristic equation. So I call it there B, but here I will already be here, so I will call it L. So what is L? L basically is A alpha 1 in the power of I plus B alpha 2 in the power of I. So, and if it's actually 0, oh, sorry, non-zero. Yeah, if it's non-zero, then our coefficients will be uniquely defined because they are basically not functions, they are just values. So then xi will be fi just divided by li. Understand? Huh? So basically, this is the case when the characteristic equation is non-zero. But if it's 0, for that specific coefficients, we would need to look at basically as a C1 plus C2 is 0. And if we will substitute it into our functional equation, we will easily can see that C1 will remain free parameter and C2 will be fixed. As you can check, it's quite easy to verify. So as you see, basically the amount of the free parameters in the equation will be equal to the multiplicity of the root. So here we assume, for example, for this specific case, that L prime of I is already non-zero. But if it's 0, then the solution, then for this specific I, it will be C1 remains arbitrary, and C2 will be already fixed, this parameter. Right. So back to our equation, because it's probably not very easy to see what I wrote here. So basically, maybe it's better to see. So this is our equation, and this is a characteristic equation, and the root is J0, 0, and this is our equivalent functional equation. So we look for the solution as this x of t is the sum C1 plus Ct. We can easily define that C2 will be fixed, and C1 will remain arbitrary. So this is an example. So now we can continue on the generalizations of the. So we can generalize the theory into the nonlinear equation. So basically, if you consider equation 8 with the kernel defined as this, and similar conditions we have for all the input data, then we can formulate this theorem 2 prime, sufficient conditions of existence and uniques of nonlinear Volterra integral equation. So the difference will be that basically we would need this J to be Lipschitz, kind of, and this condition D will be replaced by basically a bit different. Sorry. Take some water. Right. So, okay, and about the generalization. So, it's possible to generalize the theory on the systems of Volterra integral equations of the first kind. And also, recently, Professor Alfredo Lorenzi generalized this on the abstract integral operator equations in the Banach spaces. So this article is in press. And also, we generalize this also on the operator case. It's published and available in archive, like this. So now, about the numerical solution. So we just started it and have the preliminary results. So the numerical methods is not, I would say, fully ready to use, but at least some preliminary results. So basically, we use right and left rectangular rules, and basically consider this equation 9 with only 2, K1 and K2, so only one discontinuity curve, alpha. All these conditions are fulfilled. So basically, we, by applying this combination of left and right rectangular rules, getting the solution. And in the first node, so we have this the 0 x1 is like this. So basically, this guy is non-zero because of g in 0 is less than 1. So the conditions of theorem 2 are fulfilled. So, and from examples, we can observe that the method has a convergence. And so here we have the two methods. Basically, one error is defined like epsilon1 and another is epsilon2. And for where x1 hat is computed with by formula 11, like this. For in this A of T1, and x2 is a solution which is computed by formula. Oops, sorry. Yeah, I should use this by this formula 12. Right, and extrapolation is the first node. So again, we can observe quite nice results. And this is even more interesting case. So here the discontinuity is like sign. So basically, it's before we haven't used such a curves. So basically, and again, the results are quite good. Okay, so I will finish on this, and would be happy to answer your questions. Okay.
Okay, it seems not, so let's thank the speaker again.